So last week we talked about the structure of the solar system and the dynamics and how that allows us to understand the formation from the point of view of the collapse of a spinning cloud and what we end up with as a structure. But it didn't give us the whole story. And so now we're going to get into the chemistry of the system. And so here we have the abundance of elements by number of atoms in the solar system. So we can see right here that hydrogen is nearly 94% of everything by atom. It's about 75% by mass, because obviously it's the least massive element. And then helium is a small fraction. And then after that, the other 0.1% of atoms are in all the other elements, the most abundant of which oxygen, carbon, neon, and so on. And so how does this then break down for what we see in the solar system? Well, as we cool our gas, so remember we talked about how you've got the sun forming, and the sun is mostly hydrogen and helium with that 1%, or 0.1% of everything else. But then so is the gas that it's forming from. But what matters is what can exist at different temperatures. So that gas is cooling down as it's collapsing, and it radiates heat and it cools down, and at some temperature it will be able to form dust. And this is very similar to the way that soot forms. So you've got gases coming up from a flame, it's got carbon and hydrogen, and you get soot forming where it is cool enough to form. And so what we see here is that one of the first things to form is going to be aluminium oxide or aluminum oxide, because that can exist at a very high temperature. So close to the protostar you can form that. And then this alloy of iron and silicon, I think it's called kainite, anyway, that can form. And then you start to get these silicates. So this one is called forsterite, Mg2SiO4, and then aluminium silicate, and then this is iron sulfide, iron oxide, this is rust, and then carbonaceous chondrites and so on. So you can see here that the stuff that rocks are made out of can form close into the sun. This forming sun is maybe 3000 Kelvin and getting hotter, and it can form these things, but you have to get further out before you can start to form these oxides, and then you don't get carbonaceous things until you're much further out. So this is, the boiling point of water on the Earth. And then to get hydrated silicates, so that is silicates that have water in, like talc is one of those, then you've got to get down to even lower temperatures, and then to get ices like we have out in the Kuiper belt, you need to get to an even lower temperature, and so you get a gradient in what can form. But when you're out here, you can also still form all of this other stuff. This is the threshold temperature, and so out here you can form many more things than you can really close in to the solar system. And this is just another way of looking at this. And this is basically by looking at the minerals that are exist in the compositions of different planets, you can approximate its temperature. And this is done on a log-log scale, you can see. So we've got the distance from the center of the solar nebula, so basically from the sun, and the temperature at which it must have formed based on the minerals that are contained within it. And we can see that Mercury is made of these high temperature silicates and oxides, and so it formed very close in, and so we can see that you get all of the rocky planets forming close in, but you can't form any of those volatile things. Once you get out beyond the ice layer, here we have the ice layer, you get the gassy planets forming, and then out beyond that you get other ices like methane and carbon dioxide that add into what you get out in the Kuiper belt. And this is just yet another version of it. So here you've got things like tungsten, which is very rare, so isn't very useful, but aluminium oxide is a dominant thing on Mercury, and as you move out, and this one is not in log scale, so you can see how rapidly it changes, you can see that the rocky planets all have to form above about 500 Kelvin, and then as you get further out, you start to have ices, and so you get more abundant stuff. And yet again, another version of it. This one was more from the point of view of metal closest in, and then the rocky stuff, and then water ice, and then other ices as you move further out. And so, as a summary of this, the condensation sequence is basically what is the order of things that form. So close to the protostar we have refractory compounds. These are things that exist at high temperature. At very high temperatures, very close in, you don't get anything. And then as you move away, you can get the very most refractory things. And then as you get further away still, more volatile things can condense. That is, things that would normally be in gas phase at room temperature. And so you can understand the current composition of the solar system and its distribution of material in terms of the temperature drop with distance. And so it actually gives you a simple way of understanding both the chemical structure and the mass distribution. But we haven't completely understood the mass distribution, because when we look at the gas giants, they're dominated by hydrogen, helium, and in the ice giants, that is Uranus and Neptune, they are also have a lot of methane in them. And we need to, and that's partly an abundance issue. So you've got lots and lots of hydrogen, but hydrogen as a gas is too light to stay on the surface of a rocky planet like the Earth at the temperature of the Earth. But as you go out to the distance of Jupiter, a planet like the Earth could hold on to hydrogen, and there is lots and lots of hydrogen around. I'm going to reiterate that idea. But we're going to need to talk about atmospheres and how they are attained. Now, for the Jovian planets, it's not just accretion. So you get some accretion that will build up something probably approximately Earth-sized. It can be a little bigger than Earth because it can contain ices as well. So the Earth contains silicates, carbonation stuff, but as you move out, you can have the silicates and the carbonation stuff made of silicon, oxygen, magnesium, and so on. But you can also have the ices, which is made of oxygen and hydrogen, which is very abundant, and so you can make them a little bit bigger. But once you have that, you have something that forms as a seed, and gravity can capture the gases around it. Now, this will happen for the inner planets too, so you'll get the gases that are in the cloud that haven't yet formed dust or boulders will be captured. But for the inner planets, those gases get lost, and we'll get to that in the next section. Whereas for the Jovian planets, you get to retain that atmosphere, and there is so much hydrogen and helium around that dominates the mass of those planets. And so we can account for the size and mass of the Jovian planets, the gas giants and the ice giants, because of the abundance of hydrogen. So here we can see we've got the Earth is actually mostly oxygen with quite a bit of magnesium, silicon, and iron. And you can see they're more or less equally abundant. And then you've got this. But for Jupiter, it's now able to keep hydrogen, and the hydrogen is much more abundant, and so you can build this really big planet. And that's it for a basic idea. Actually, I'm going to back up very slightly, because the other issue is that because you've got a seed and you're now collapsing gas down onto the Jovian planet, it essentially forms like a mini solar system, which is why planets like Jupiter and Saturn have so many moons, that you're now forming another little disk of gas from which you form little planets. And so Jupiter is like a mini solar system with Jupiter as the star and all its moons as planets. And so you can actually explain the fact that those objects have a large number of moons, most of which are in the same plane, by following this model.